Machine learning can be used to derive insights from huge amounts of data in our respective fields, especially if it's something we can't just look up quickly. Having computers that learn from our examples and build recipes called models helps us automate the process of finding insights and with great accuracy. Now, ML isn't magic. It's designed to give you results on the specific thing you trained it on and nothing else. However, let's be honest, the traditional path for learning ML can take you hundreds of hours to ramp up on, and currently requires experimenting with different algorithms via trial and error until you find one that gives you the results you like. And yet there is great urgency to accelerate our work in meaningful areas, such as climate-based solutions. And so in this episode, we will dive a bit deeper into how we use our favorite generalist ML technique that we use in this People on Planet AI series. Out of the many ML algorithms out there, I'm happy to share that deep learning is a technique that can be used for almost any supervised learning job. In supervised learning, you tell a computer the right answers to look for through examples. Deep learning is very flexible and is a great go-to algorithm, especially for images, audio, or video files, which are types of multidimensional data. This is because each of these data types have one or more dimensions with specific values for each point. More specifically, images are a collection of red, green, and blue, or RGB values across a 2D space. Audio has a wave amplitude across time. Video also has RGB values, but across space and time. For example, training a model to classify tree species from satellite images is a kind of image segmentation problem, which is classifying every pixel in an image. However, satellite sensors collect a wider range of bands than the typical images based on the 3 RGB channels. In contrast to traditional computer science, programming is kind of like a glorified calculator. We may approach this problem by writing a function with explicit and sequential steps that review every single pixel one by one for every image. This is quite prone to errors, which makes it hard to maintain. It also uses loads of computing resources and hours. Because of all of this, it's also really expensive. On top of this, if you then wish to modify the function to include another type of tree species, you may have to rewrite your function altogether. This is where training an ML model via deep learning can greatly simplify things. Instead of handcrafting every instruction, you give image examples with labels of tree species to the computer and let it learn from them. And when you want to find more tree species, it's as simple as adding new images and retraining the model. With that reference in mind, let's dive a bit deeper into how deep learning works with a specific example. Let's say you want to compare satellite images in different years to see where deforestation is happening in your supply chain. Note that a machine learning model is like a function that takes input data, transforms it, and returns us something else, such as the classification label of where there is a tree or no tree. Or it could also give us the magnitude of a value, like the density of tree canopy, which is known as regression. To begin, we will need a dataset that includes satellite images that have labels of where there are trees and where there aren't. Now, machine learning only understands tensors, which are numbers stored as an array or vector in one dimension, or as a matrix or table in 2 dimensions, or as multidimensional data. With this in mind, we convert satellite images into tensors where each pixel has one number for every satellite band. We have to frame our model differently depending on our goal. Here are a few common goals. Regression, which predicts a number. Binary classification, which makes a prediction between 2 categories. multi-class classification, which classifies things across multiple categories. Semantic segmentation classifies every pixel in an image, and embeddings, which groups similar elements into a multi-dimensional space. In our case, we simply want to know if there are trees or not for every pixel, so this would be a binary semantic segmentation problem. We then expect the outputs to be the probabilities of trees for every pixel as a number between 0 and 1. 0 representing no trees, and 1 represents a high confidence in trees. But how do we go from input images into probabilities of trees? Well, think about it this way. A model is a collection of interconnected layers. At each layer, data is transformed. And based on our desired outputs, we must come up with an arrangement of layers that transform our input data into our desired outputs. The first layer of ingesting data is called the pre-processing or normalization layer. This is because machine learning doesn't like large numbers, so we have to transform input data into smaller numbers at this first layer. After that, there are many layers we can choose from, kind of like Legos. These dictate the model's architecture. Here are the common ones. Dense layers. These interconnect all the output from the previous layer to all the inputs in the next layer. Convolutional layers. These look at the surrounding patch of input values and connect them to the next layer. Deconvolutional layers. These project the value into a patch of values in the next layer. Pooling layers. These aggregate values into the next layer. Each layer, by the way, has something called an activation function, which transforms the outputs of each layer before it passes them to the next layer. Going back to our deforestation use case in supply chains, after that first layer of preprocessing an input image, we then add a 2D convolutional layer followed by a deconvolutional layer, which gives us a total of 3 layers so far. We could add more layers, by the way, but this is a good starting point. We then reach the 4th and last layer. Depending on our goals at the beginning, we choose an appropriate loss function that helps us score how well the model did during training. A larger loss, for example, means it has room for improvement. The model adjusts to do better the next time it sees that example. Here's a handy-dandy table, by the way, with our recommended activation and loss functions to choose from based on your goal. We hope this saves you time. For our use case, because we use binary semantic segmentation, we choose to use a dense layer with a single output at that last layer. This helps classify every pixel in satellite images with a value between 0 and 1. We also choose a sigmoid activation function and an IOU loss function. Now that we have a model and have some examples to teach it, we're ready to train our model. Ideally, we want to split our training examples into 2 datasets. One is for the model to train on and learn from. The other validates how well the model did on data it has never seen before. If the model does well with the training dataset, by the way, but not with the validation dataset, it might be overfit, meaning that it memorized the training examples. But providing it with more training data or adding more layers could help. Overall, this was a super quick summary to help demystify why we use neural networks in our People on Planet AI developer series. We also hope this inspires you to build sustainability use cases with deep learning. If you would like to review this process in greater detail, I have linked in the description below a blog post and several helpful resources. And community, if you found this content helpful, you can follow us further on this journey. Cheers.